Alright guys, in this video what I want to do is talk to you about heat transfer. So hopefully you've had time to go over some of the materials, to look at heat transfer and some different ways that heat can be transferred from one area to another, right? But basically the goal of the universe is for everything and everyone to be the exact same temperature, then it's nice and happy, right? So if I put an ice cube out on the counter where it is warm outside, the universe is like, no, that thing is cold, the air around it is warm, let's even that out. Okay, similarly, if you put a glass of water um, and pour it over ice, right, the universe says the same thing, like, no, this water is warmer, this ice is colder, let's get all of these things somehow to one happy medium temperature, right? So these are just sort of the mechanisms that we're looking at when this happens. So there are three main mechanisms, okay? And I want to talk about them in terms of their rank. So pretty much the relative speed, okay? Now I'm going to emphasize this. This does not mean that one is will only give you a small amount of heat and one will give you a large amount of heat. This is just that if you compared them all, this is how they would generally rank. So our first, or you know what, I'm going to start with the third. Okay, so the slowest way to transfer heat from one place to another, relatively speaking, is by radiation. Okay, so radiation will transfer heat pretty much anytime. No, even if there's no atmosphere, there's nothing, radiation will still transfer heat. So it's kind of the most robust of the three. It will always work, but it is the slowest of the three mechanisms that we're looking at. Okay, so think of the sun, right? So we are getting heat from the sun primarily through radiation. Okay, there is no actually point of contact between us and the sun, thankfully. The sun's heat is just radiated towards us. Okay, more so in South Texas than other places. So, moving on, we have two other mechanisms to talk about. The second ranked of faster than radiation. If you want to transfer heat faster than radiation, one thing you could do is you can use convection. Okay, so when you use convection, okay, you might think, all right, a convection oven, you might have heard this term before. A regular oven might use primarily radiation, right? Because when you put it in, when you put something in the oven, we've got some heating element. It's not touching whatever you're trying to heat. So the heat has to radiate from the element towards whatever the food or whatever you're trying to heat up in the oven, right? But there is actually usually some convection going on already in your oven, even if you don't have a quote-unquote convection oven. The only thing with a convection oven is they try to maximize this actually going on. So what is this? In your oven, let's say we had our oven here, and we have our heating element at the bottom, and then we've got our food. That's turkey. Well, that was pretty good. That was a good turkey. Okay, so we got a turkey, the heating element. What my convection oven will do is it'll try to circulate some air, okay, and move the air around. So convection is moving heat by actually moving air, right? So let's say the element might heat up the air that's right next to the element, but then if we move this air, if we carry it over, then that hot air can heat other things in tiny bursts by touching them, by touching directly. Okay? So this is actually just a midway point between our third ranked and our first ranked, which is, you guys probably guessed it already, this is conduction. Okay. Convection, what I'm doing is I'm taking this air that's, let's say, touching the elements, I'm pushing it over and making it touch the chicken. When they touch, then those two things are in contact. They're in conduction, right? So that's the best way to actually transfer heat, okay? Again, this is not saying that radiation will give you a small amount of heat while conduction will give you a large amount of heat, right? You think about if you compare touching, something, a hot surface versus radiation, you might have a lot more radiation, but just if we take everything the same, conduction will always be the fastest. For example, the sun is radiating a bunch of heat, okay? But if we take the same object, the sun, and we look at conduction, if you were to touch the sun, you would get way more heat out of it than if you were to look at radiation, right? So this is just a rank, but you can still get a bunch of heat out from radiation or convection, right? Okay, so now that we have our three methods here, the one that I want you guys to focus on when we're looking at this is conduction. There's going to be some formulas here for conduction, for convection, radiation. We can use all of these kind of formulas to describe how heat transfers and how heat moves. But for now, I want to focus on conduction because it's actually a really good case for us to look at building formulas. I want you guys to be confident at this point, you guys are physicists now, that you can try to build your own formulas when you don't have one, right? So for example, if I want to look at conduction, okay, let's say I have an electric stove burner, okay, and then we've got an object. It could be my hand, okay, it could be a fork. A fork looks just like my hand. I'm not sure what's going on here. Okay, it could be any object. And we want to look at what are the things that affect how much heat is going to be transferred, right? So I've got a few of them listed here, and these might make sense to you, right? So just think of if you were to touch a very hot surface like the stove, which one of these would result in you having a worse time, right? So first of all, we have the amount of time these two things are in contact. This one right away, right? So if you lightly tap a very hot object, you might hurt a little bit, might sting a little bit, but it's nowhere near as bad as if you were to lay your hand right on that element and just keep it there, right? Or lay this fork that you're holding right on that element and just keep it there. Eventually, this is going to be, a very bad day for you. So when we look at this, what we want to do is, let's use another color here, is say that if I increase time, then I'm not going to call this temperature, I'm going to call this heat. The amount of heat will increase, right? If I increase the amount of time I'm in contact, the amount of heat I transfer will increase as well, okay? Secondarily, the temperature difference. Of course, if this thing is on low and you touch it versus if it's on high all the way and you touch it, all right? So those two things are very different situations, right? So if I look at this and I increase the temperature difference, let's say my hand is a fixed temperature, so all I do is I increase the temperature of this element, what will happen when we look at how much heat is transferred while we're touching? Well, the heat will go up, right? Now, this one is a little bit weird, but it'll make sense when we kind of unjargonify it, right? So take out the jargon. So right now I have cross-sectional area of whatever the conductor is, right? So pretty much this just means how thick is, or how much contact do we have between the object and yourself, right? So for example, if I'm holding a fork, if I just lay one corner of this fork on the heating element, okay, or if I just take this entire fork, just right cross section right here, the whole width of this fork, and I just shove it right onto that heating element, which one is going to transfer more heat, right? Or you might think of this, if you use a very thin fork or maybe something very, very thick, right? So the thicker item will be able to transfer more heat. Same thing, the way I usually remember this, guys, whenever I'm cooking, is if you touched with just the pad of just one finger, all right, on a very hot surface, versus if you grabbed it with your entire hand, right? Even if you stayed the same amount of time, one is much worse than the other, right? So one lets heat pour into you much faster or much more heat than if you were to use just one finger, right? So here, if I increase the amount of area of contact, then I'll also increase the heat. The only thing here, we see all of these things are bad news for us so far, okay? So the only thing here is this last one, the distance between the source and the destination, right? What is the distance between you and the element when you touch it directly? It's 0, right? And that's the worst possible scenario for everybody, okay? If you use a fork, this is better, right? It's maybe not great, but it's better. So I have, I can use the fork. Now, the other thing is that I could use a really, really long fork. So let's get another fork in here and just make it super long, okay? And then at the end here, I'll hold on to this fork, okay? So in this case, this is much better. I like this better than this, and of course, I like this short fork better, way better than just touching it directly, right? Because what I'm doing is I'm increasing the distance between the hot thing and my hand, right? The thing that I don't want to burn. So here, now we finally get some good news where if I increase the length, right, then what I do is I decrease the amount of heat that is poured in. So finally we get something where if we increase it, we are reducing our heat. But there's actually one more thing, guys. Now, I have a number 5 here. So I want you guys to look at this. We're just talking about touching this with a fork. But what if you touch this with all right. So this is a stick. Let's make this a little more clear. This is a stick. This is a fork. Okay? So these two things can be the same length, but which one would you rather touch a very hot object with? A metal fork or a wooden stick? Okay? Probably the wooden stick. So why is that? So this is actually related to conductivity of the conductor, the thing that is transferring the heat. Okay, and sadly here, if we increase the conductivity, right, so like metal is more conductive than wood, we also increase the heat. So let's just take all these things and let's just line them up the way that they are, right? So I have this already down here, but if I say my heat, it's going to be proportional to everything that is directly like up and up, up and up, up and up. These go on the top, right? So I'm going to have, something like time, temperature difference, cross-sectional area, conductivity, we'll call this like K, and we're going to divide this, so we're going to put on the denominator, we'll put anything that is opposite, right? Inversely correlated. So these things are opposite of each other, where if you increase one, you decrease this one. So in this one, we'll put L on the bottom. Right? So we've kind of built this formula. Even if we're missing kind of a piece of it, this will give us a really good idea of something, even if we leave something out, we'll start to get a feel for what are the factors that influence heat transfer or anything, right? Anything we use to build the formula. We just think of what are the parts and how are they related to each other, okay? Pretty much we can do them simply like this. If I increase this, what happens to this? If I increase this, will this decrease, right? We ask these questions and we can start to build up our own simple formula like this. And just so it happens, it turns out, I mean, I already knew this, so it's easy to build this out. But this is our formula. It's exactly the same thing. It's just shuffled around where I have my conductivity, and here I have my cross-sectional area, my difference in temperature, the amount of time we're in contact, and the length of my conductor, okay? So putting all these together, this is my formula for amount of heat during conduction, right? So take care of this. Let's just use this one here. So this will be the formula that you guys use when you're calculating amount of heat conducted during some contact between objects. All right, guys. So let's go ahead and take these formulas and take these new concepts and do some work for the transfer of heat